Okay, students, up to this we have learned about the solid fluid catalytic reactions where actually there is a two reactants are there and one catalyst is present to enhance the reaction rate or decrease the reaction rate, and then the product is formed. But for the case of non-catalytic reactions, there is no catalyst actually used. Whatever the solid particles, these are actually involved in the reactions, and another portion will be the fluid portion. So that fluid can be either gas phase or the liquid phase. So for this purpose, you can follow the book Chemical Reaction Engineering by Octave Levenspiel. Now go to the next slide, that is, first we should know that what are the key features for the solid fluid non-catalytic reaction. So as I told you, there are two phases are involved. One is solid phase, which is actually involved in the reaction. Another one is fluid phase. The fluid can be either gas or liquid phase. So that's why it is a heterogeneous type of reactions. And the reactants come, what will happen, the reactants in the bulk phase, bulk fluid, suppose the reactant is A, it comes contact with the solid surface, solid core surface, and which is actually not a catalyst, and reactions happens and form product. So this is the non-catalytic solid core. Fluid A is comes to the solid core and the surface reaction is happens and the product is comes out from the solid particles. So the product may be fluid, solid, or the mixture of the solid fluid. Now this type of reactions can be happen in two types, two methods. One is progressive core model, that is called as a PC model, where the size is constant, so size remain same. Another one is shrinking core model. This is actually known as SC model, where the size is gradually decreased as the reactions time is going on. The size is gradually decreased. Now, for most of the non-catalytic reaction, this shrinking core model is highly acceptable model rather than the progressive core model. Now, come to the progressive core model first. So, what is actually progressive core model and why the size remains same? So, as I told you that progressive core model is the size remains constant. Now here gas or liquid, whatever the fluid is there, gradually goes inside and the reactions occurs gradually and converted the product, but the size is not changed. Now if you see the picture, what you see here, so initially it is unreacted particle. Initially it is an unreacted particle at time t is equals to 0. Now as the time is going on, you can see here, as the time is going on, so gradually the sizes remain same, but the solid particles, which is actually in the white color, it is converted to the products gradually, and more time is going on, the product is formation is more and more. So here the blackish color, the darkness of the blackish color is represents that the conversion, how much conversion is actually happens. So as the time is going on, you can see here the blackish color is much more higher. But so you can see here the completely reacted particle, it is the completely reacted particles. It is a hard and firm unchanged size. The particle is very much hard and the size is not changed at all. So as the time reaction is going on, though the conversion is fully the particles reactant particles is converted to the full conversion is their product, but the size is remains same. Now go to the next part. Now why the size is remain same? So there are two possibilities. One is when the solid particles contains more and more lots of impurities. In that case, what will happen? These impurities are tightly bound to the solid core. So when the impurities are there, it remains as a non-flaking ash, and but the reaction is processed inside the core. And what will happen is this impurity is actually responsible to keep the particle size, shape and size same. So more and more impurities means your it may follow the progressive core model. So that impurities actually mainly responsible to keep the size remain same. Now other possibilities is what? Sometimes though the impurities is not there in the solid particles, the whatever the solid it produced, that is firmly bound to the core, which may also preserve the shape and size of the solid particle. So these are the three two possibilities which may actually help to remains the uh, size of the particle same. Now these are the few examples. So roasting of the ore is a very good example for the progressive core model. Now here you can see that ZNS is the zinc sulfide is the ore, and ore is converted to the zinc oxide. Now here you can see that ZNS is a particle spherical particle which is reacted with the oxygen, and that oxygen is actually available in the air, and that ZNS is totally converted to the ZNO, though the ZNS size and the ZNO size will be remain same. So most of the roasting phenomena, roasting reaction is happens in that category, falls in that category. Now another example is preparation of iron oxide and preparation of the irons, production of the irons. So Fe2 is reacted with the oxygen and forms the Fe2O3, and another example is Fe3O4 is hydrogenation of the Fe3O4 to form the iron. Okay, so these are the few examples as given which is actually applicable for the progressive core model, where the size is actually not changed, whatever the solid particles, and this is the gas fluid, and whatever this size and the iron size will be same. Now clearly you can see here in this example is a solid product which is formed and get deposited on the solid core, in which fully fluid solid non-catalytic reactions occurs and this helps in the preserving the size of the core. Sorry. So this is the concentration profile is given to you. That is, you can see here. Initially, there is an unreacted core, or you may say a very low conversion. A slight ash color is there. Then blackish is gradually increases. Blackness is gradually increases. So that blackness is actually represent the conversion. How much the product, reactant is converted to the product. So it is a low conversion, you can see it is a high conversion rate. As the time is going on, the size remains same, but the reactant concentration is gradually decreasing from this portion to this portion and to this portion, but you can see here the size is from R to R. If you consider the radius of the spherical particle is R, this side is R and this side is R. So from R to R the concentration is the R to R is same, the size is same, but the concentration is gradually decreased. Now go to the next portion, that is shrinking core model. So come to the next point, that is shrinking core model, where the size is gradually reduced. Now as the time goes on, the core is getting consumed and then dispersed. Core is getting consumed, and what will happen afterwards? It is getting dispersed, and mostly it is forms as a ash, and it may form the gas. It may form the gas. Okay, so this type of reactions occurs when there is a reaction that involves carbonaceous. Mostly the carbonaceous materials which are oxidized, they are mostly follow this category, falls in this category. So what will happen here? The some assumptions are taken in this model. Reactions occur at the first in the outer skin. Reaction does not occur everywhere. Only the outer skin is the reactions happen only the outer skin. Reaction zone moves inward towards this direction, inward direction. The reaction happens towards the inward direction and leaves behind completely converted material or inert solid. So you can see here in the picture. So initially it is an unreacted particle at T is equals to 0. As the time is going on, what will happen? You can see here, either it may forms the ash flake, that is a ash flakes, which may actually comes out from the solid core. It is not tightly bound. That ash is actually not tightly bound to the core part, solid core. It is get deposited. It is separated from the solid core, and or some portion is actually converted to the gas, which may again go to the air. Okay. So mostly the good example is actually the carbon burning. Carbon burning, what will happen? Carbon is burnt, and it may form the CO2 and CO, which actually goes to the few acids, whatever the impurities are present in the coal, these are actually converted to the ash, and most of the carbon is converted to the CO and CO2. So this is the best example for the shrinking core model. Now these are the examples, that is production of the producer gas. Carbon is oxidized and form the CO2, CO, and also if you use instead of oxygen, if you can use the steam, instead of gas, you can, if you use the steam, then also it can produce CO, CO2 and hydrogen. Okay, so CO and hydrogen is the producer gas. Now this is the concentration profile, you can see here. So as the time is going on, uh, here you can see that this is a lower conversion and this is the higher conversion, and here the ash layer, this is the ash layer, and this is the unreacted core. So as the time is going on, you can see here the unreacted core radius is gradually getting decreased and decreased, and certain time it will be disappeared. Okay, so what will happen? You can see the concentration profile will be the it will be the sizes is from this to this portion. Okay, so here it is R, total radius is, the core radius is actually, the solid particle radius is from this, if you consider this is the center, and from this to this it is R. But the initially at low conversion, as few reactions happens, few conversions happens, so reactant size, the particle sizes get reduced, and it comes to this portion. Okay, and the concentration, you can see here, it goes from this to like this. Okay, so as you can see here, as the time is going on, the radius is gradually decreased, but the concentration, the core reactant concentration is fixed. The reactant concentration is fixed, because here whatever the concentration is here, the concentration will be the same here, and the concentration will be the same here. Only the changes will be whatever only the changes will be the size, because the assumptions was, if you go to the previous slide, you can see that assumption is the reactions happens only on the outer surface, and the reaction is towards the inward directions. So though the reaction is happens going gradually the conversion is happens, still in that core the concentration of the reactant will be the same. Okay, only the sizes is getting reduced, the core sizes is getting reduced. Now in this solid fluid reactions, mainly three processes are involved: the diffusion through gas film, so this is the gas film, diffusion through the ash layer, and the reactions happens at the unreacted core surface. So one is diffuse. First, the reactant A is get diffused from bulk gas layer to up to the ash layer, then ash layer to the unreacted core, and then the reactions happens at the surface of the unreacted core. So whenever we are trying to determine the extent of the reaction, therefore the extent of the reactions that is the overall conversion of the reactant of the solid depends upon the which will be the rate limiting step, whether the diffusion of the diffusion of reactant A from the gas layer will be the rate limiting step, or diffusion from the ash layer, or the interface surface reaction, that will be the rate limiting step. So based on this, what will be the rate limiting step, we can find out that how much time is required for the conversion of the reaction or total conversion of the reactions. So we'll discuss this part in the next lecture. So today is up to this. Thank you.